In this module, I'll be discussing how air pollution control devices are designed. There are 5 mechanisms that can be applied to remove particulates from a gas phase: sedimentation, impaction, which is commonly known as a cyclone, filtration, liquid scrubbing, which uses a Venturi valve, and electrostatic precipitation. We'll cover each of these briefly. Sedimentation is used to remove particles that are large enough to settle under the force of gravity. This is appropriate for particles greater than 100 microns in diameter. It is often used as a pre-treatment because it is fairly inexpensive. The effectiveness of this is dependent on the velocity of the particles relative to the critical velocity of the airstream. We would have discussed this in water as the overflow velocity versus the settling velocity of a particle. And the same principle applies. You have the settling velocity of the particle and you have the upward velocity of your gas stream. The second method is to use impaction or centrifugal force to remove particles in cyclones. The principle here is that an airstream carrying particles changes direction. As it approaches a wall, plate, or fiber, the momentum or inertia of the particles in that airstream is different than the momentum of the gas stream. The particles strike or impact the surface and fall down. So you'll have a centrifugal force, and you'll have a particle traveling this that will move at a different velocity than the bulk stream, and when it hits the wall of your control device, it will fall out. This can be very effective for particles of diameter greater than 10 microns. Here I show you a picture of a cyclone. As you can see, the gas would enter in the inlet here, which is going to have a fairly small diameter. And so it's going to move at a high velocity through this chamber. As the gas enters, it's going to be forced around through a spiral motion, and then it's going to come out the top. Now, as the particle traveling through this impacts the wall, it's going to be moving at a different velocity. It will impact the wall, and it will fall out and be collected in the bottom of the hopper. Typical cyclones range 3 to 5 feet in diameter, and high efficiency ones are around 8 to 12 inches in diameter. The efficiency of particle removal increases as the diameter of the cyclone decreases. As the diameter of the cyclone decreases, the velocity of the gas stream increases because it's moving through that smaller diameter. This creates the higher efficiency case. The size or density of the particles also increases the efficiency. As the size or density increases, the better the removal of those particulates. And then with the decreased diameter, you have that increased gas velocity, and that also creates higher efficiency. The operational problems that are common with cyclones are that there is a high pressure drop across the system, and so you need to limit that pressure drop as much as possible. And finally, they can be prone to plugging with a large amount of solids that are damp, clog that hopper, that outlet, especially if you're using a high efficiency system which has a small diameter. The second system, or rather the third system, is filtration. This is extremely common in household and office place settings. A particle is filtered out physically by being intercepted by fibers or by the electrostatic attraction to the fiber. The particle interacts with the surface where it adheres due to physical or chemical forces. It is commonly used for smaller diameter particles, less than 5 microns. 2 options are typically used. The first is a deep bed filter, which is what we use in our homes for our air conditioning and furnace filters. They produce relatively clean gas at low volumes, and when the filter is spent, you throw it away. This is why these are most common for households where a fairly small volume is passed through. For larger school place buildings or industry, baghouse filters are more common. These are used for higher volume flow-throughs. Once a dust cake forms on the fabric and a pressure drop reduces the gas flow rate to an unacceptable level, filter bags must be cleaned. Cleaning can either be performed mechanically, by reversing the airflow, or by doing a pulse jet cleaning. This is the picture from your textbook of a baghouse. A baghouse simply has different filter bags, thus the baghouse, and air is pushed through these bags. So here you have your air that's going to push through that bag. It's going to have a lot of opportunity for those particles to interact with the bag, to be intercepted by the material, and clean gas flows out. If mechanical shaking is used, 2 of these units would be placed next to each other, and every 30 minutes to an hour, the bag would be taken offline, meaning airflow to it would be redirected to the redundant unit, and the bag would be mechanically shaken. The particles would fall down into the hopper and be removed. Pulse jet cleaning can also be performed. It's the same dirty gas coming in and going through the bags, but in a pulse jet system, when this is stopped, and that could happen very quickly, perhaps every 2 to 15 minutes, then your air cleaning jets come on, which are located here, and they reverse flow through that bag. This is a very high pressure, fast velocity flow, similar to backwashing a water filter. This takes more energy, but the plus is that you don't need to take the baghouse offline to perform this cleaning. The next unit is the liquid scrubber. Liquid scrubbing combines sorption processes of a spray chamber with the impaction force of a cyclone. These are a great option for wet, corrosive, or hot particulate gas streams. The corrosive nature and the wet nature of these gas streams would negate the use of fabric filters, such as a baghouse or a deep bed filter. And so what happens here is your gas comes into a Venturi valve. What happens through this Venturi valve is that gas is pushed through a small diameter, which increases the velocity as it goes into the next step of this. It creates that high velocity. While that's occurring, we're also going to inject liquid. And so this part of the chamber is the spray chamber or the scrubber. You're going to get some absorption through this. And as this moves into the cyclone part of the unit, it's going to create that impaction factor for the particulate. The last unit we'll review is the electrostatic precipitator. In this system, gases pass through wires or plates that are producing a direct current. If the gases have any ionic or electrical property, and most commonly those are negatively charged ions, then those negatively charged ions will migrate to the positively charged plate or wire. So this depends on electrophoretic mobility. For this to work and be efficient, the gas velocity moving through those plates has to be fairly low. That way, the electrical charge can act upon those particles and encourage movement, electrical charge movement, electrical interaction. Once particles move to the plate, the oppositely charged plate, periodically those plates will get covered, and a simple tapping at frequent intervals releases those electrically attracted particles to a hopper. This is commonly used to remove fly ash from furnaces burning fossil fuels. The presence of sulfur dioxide often aids particulate removal in these electrostatic precipitators. Here's the picture from your textbook. If we look at the plate, these plates would be positively charged, each one of them, and your gas flowing through this at a low velocity would be negatively charged. As the gas passes through the plates, and the distance between these plates needs to be very small so that you can have that electrical attraction and movement. Then the particle would be attracted to the plate, and every once in a while it would be tapped, and those particles would drop out to a hopper. In class, I'll give you certain characteristics of common gas streams, and we'll work on picking out the appropriate control technology for those streams.